Okay, this video is about introduction to functions. Before we talk about the definition of a function, we need to know what the definition of a relation is. A relation is a set of connections between objects in a set, in an input set called domain, and an input and an output set called range. So a relation is a set or a collection of connections or associations between two sets. One set that is the input set called domain, and the other set that is the output set called the range. Let's look at some diagrams. There are four types of relations. We have one-to-one relations. It means that in this type of relation you have any object in the domain or the input set is connected only to one and only one object in the range. So for example, the triangle is connected only and only to 1. The star is connected only and only to 2. And the circle is connected only and only to 3. And you have the same thing from the other side. So any object in the range is connected to one and only one object in the domain. So 1 is connected only and only to triangle, 2 is connected only and only to star, and 3 is connected only and only to circle. So this is a one-to-one relation. You can also have a many-to-one relation. So in a many-to-one relation, 2 or 3 or more objects from the domain can be connected to just one object in the range. Like in this case, the triangle and the star are both connected to 1. Circle is only connected to 2. So this is a many-to-one relation. You can also have a one-to-many relation. In a one-to-many relation, one object from the domain can be connected to more than one object in the range. Like for example, the triangle here is connected to 1 and 2, which are two different objects from the range. So this is a one-to-many relation. A relation can also be many-to-many. So this means that one object from the domain can be connected to more than one object from the range, and one object from the range can be connected to more than one object in the range. So there are four types of relations: one-to-one, many-to-one, one-to-many, and many-to-many. Now, what's a function? A function is a relation that is either one-to-one or many-to-one. So of these four types of relations, this one is a function, this one is also a function, and these two are not functions. A one-to-one relation is a function, a many-to-one relation is also a function, but a one-to-many relation is not a function, a many-to-many relation is not a function. So here we have an example of a one-to-one function. So this collection here is the domain, this collection here is a range. The values from the domain are conventionally represented by x, and the values from the range are conventionally expressed or indicated by y. So you see 1 is associated to 2, 2 is associated to 4, and 3 in the domain is associated to 6 in the range. So this is called an association diagram. That's one way of representing a function. Another way of representing a function is using a table. So you have a table with two rows. The first row is for the values of x, values from the domain, and the second row is for the values from the range. 1 is associated to 2, 2 to 4, and 3 to 6. You can also put these pairs inside a collection and represent a function as a collection or a set of ordered pairs. So you have 1, 2, 3 ordered pairs, 1, 2, 2, 4, and 3, 6. You can also graph these points or these ordered pairs on a rectangular coordinate system, and that would be another representation of a function. So you graph the points 1, 2, 2, 4, and 3, 6. It is also a representation of a function. And sometimes you can find a pattern. Like here, you can see that any value in the domain is associated to double its value in the range. 1 times 2 is 2, 2 times 2 is 4, and 3 times 2 is 6. So you can represent this function as this algebraic equation as well. F of x is 2x. F of x is another way of representing y, or a value from the range. So f of x is a value from the range associated to x from the domain. So that's the meaning of f of x, the value from the range that is associated to x in the domain. So if x is 1, f of x is 2 times 1, so 2. If x is 2, f of x is 2 times 2, so 4. And if x is 3, f of x is 2 times 3, that is 6. Here you have to indicate the domain. The domain of f, so that's the notation, d of f. The domain of f is the set of 3 numbers, 1, 2, and 3. So these are 5 different representations of the same function. Now let's take a look at a many-to-one relation, which is also a function. Now this is a association diagram of a many-to-one relation. You see 0 is associated to 0, 1 and -1 are associated to 1, 2 and -2 are both associated to 4. This is the domain, this is the range. We use x to represent values from the domain, we use y to represent values from the range. You can also represent this as a table. So 0, 0, 1, 1, -1, 1, 2, 4, -2, and 4. You can put all these ordered pairs in one collection and represent your function as a set or a collection of ordered pairs. So that's another way of representing a function. You can graph all these points on the coordinate system. These are the 5 points: 0, 0, 1, 1, -1, 1, 2, 4, and -2, 4. And this is another way of representing the function. Or you can notice that here each value from the domain is associated to that value times itself from the range. So 0 times itself is 0, 1 times itself 1, -1 times itself 1, 2 times itself 4, -2 times itself 4. So you can represent this function as an algebraic equation, f of x equals x squared. What does that mean? It means that whatever value x from the domain is associated to x squared in the range. So f of x is actually y. You have to indicate that the domain is 0, plus minus 1, and plus minus 2. So a one-to-one relation is a function, a many-to-one relation is a function, but a one-to-many relation is not a function. So you have this type of problems. Determine whether this collection of ordered pairs is a function. You're given a set of ordered pairs. In this case, you're given 5 ordered pairs. The easiest way of solving this problem is drawing the association diagram. So first you find the domain. The domain is -1, 1, and 2. -1 is repeated, but it is here, it is also here. But when you are drawing your domain, you're not going to repeat 1 because these are sets and repetition does not count. So -1, 1, and 2, you put that in the domain, and then you have 0, 3, 5, and 7. You put them all in the range, and then for each ordered pair, you have an arrow to indicate the connection. So -1 is connected to 0, 1 is connected to 3, 1 is also connected to 7, 2 is connected to 5. As you can see, I have an instance of one value in the domain being connected to 2 values in the range. This makes it a one-to-many relation, and a one-to-many relation is not a function. So no, this is not a function. Another example, a many-to-many relation is not a function. So determine whether this collection of ordered pairs is a function. You're given a collection of 5 points. Same strategy, you draw the association diagram. The range, the domain is -1, 0, 1. -1 is repeated, 1 is repeated, but you're not going to repeat that because otherwise you wouldn't be able to see whether it's a many-to-one or a one-to-many relation. Just -1, 0, and 1 in the domain, 2, 3, and 5 in the range. Again, for example, 3 has been repeated, but you're not going to repeat that in the range, in the association diagram. You connect using arrows, and then it becomes evident that this is a many-to-many relation. -1 is associated to -1 from the domain is associated to 2 numbers in the range, and 2 in the range is associated to 2 numbers from the domain. This means it's a many-to-many relation. A many-to-many relation is not a function. Okay, we have a test for checking whether a graph of a relation is the graph of a function. This is called the vertical line test. And this test says no vertical line intersects with the graph of a function more than once. So if this graph is the graph of a function, no vertical line should intersect with the graph more than once. But clearly, if I draw this vertical line here, I see it intersects with the graph here and also here. So this is not the graph of a function. This is a relation that is one-to-many. So for example, you see this value of x has been associated to these 2 values of y. For example, if I draw this other vertical line, I see this one also intersects with the graph more than once. So it's clear that these 2 points, 4, 2 and 4, -2, are both part of this graph. This is the point 4, 2, and this is the point 4, -2. So you see one value from the domain 4 is associated to 2 values, 2 and -2, from the range. This means that this is not a function because it's a one-to-many relation. And this is exactly what the vertical line test does. It checks whether you get 2 different values of y for the same value of x. But this other one here, it is a function because I cannot find any vertical line that intersects with the graph more than once. So whatever vertical line that I can think of intersects with the graph only once. This means that this other one here is a function. So if you are given the graph of a relation, you want to check whether it is a function or not, you just try to find a vertical line that intersects with the graph more than once. If you're able to find such a vertical line, it's not a function. So for example, here, this one is not a function because think about this vertical line here. This vertical line here intersects with the graph here and also here, so this is not a function. But this other one, I cannot think of any vertical line that intersects with the graph more than once. This means that the graph to the left is a function. You can also view a function as a machine. That's also useful in many applications and many problems that we solve. A function is a machine that associates any input x to one and only one output y. The set of all possible input to a function is called the domain, and the set of all the possible output from a function is called the range. So think of the bathroom scale as a machine, which is also a function. So what is the domain of this machine? The domain of this machine is all the possible input. All the possible input for a scale is all tangible objects. What is the range? The range is all the possible output. And what is the output from a scale? The output from a scale is weight, which is a positive number. So the domain is all the tangible objects, and the range is all the positive numbers. So this is a function that associates any object into its weight. So you can see that this is a this is a many-to-one function. Why is it many-to-one? Because it's possible for two different objects or three different objects from the domain to have the same weight. So 2 or 3 or 4 or even 1,000 different objects from the domain can be associated to only one object in the range. So it's a many-to-one relation. So it's a function. It's impossible for one object to have two different weights. Each object has one and only one weight. This makes this a function. So no object in the domain is associated to more than one object in the range. So it's not one-to-many. It's just a many-to-one relation, which is a function. Another example. This is a function that is one-to-one. A biometric device that associates a human fingerprint to a unique code. So what is the domain of this function? All the possible human fingerprints. What is the range? All the possible unique codes. For example, all the possible social insurance numbers. You can see that this is a one-to-one relation because each fingerprint is associated to one and only one unique code, and each unique code is associated to one and only one fingerprint. So that makes this a one-to-one function. So this is a machine that accepts a fingerprint as an input. It produces a unique code as the output. Okay, let's take a look at some examples. Given the function f of x equals 2x minus 1, evaluate f of -1, f of 2, and f of a plus 3. Okay, first, what does this mean, f of x equals 2x minus 1? It means that we have a function that receives a value x as input, doubles that, and then subtracts 1 from that and returns the value as output. So whatever value you give this function, it will double that and then subtract 1 from that. So for example, if you give it -1, it will double that and then subtract 1 from it, and it will give you -3 as output. So you see, the value that you have here within parentheses, you are gonna replace that, you're gonna plug that into the function. That is, all the instances of x should be replaced with this value here. So for example, what is f of 2? F of 2, you have to replace x with 2. So it's 2 times 2 minus 1, that is 4 minus 1, which is 3. Part A also asks for f of 2. But we already know what f of 2 is. We calculated f of 2, and f of 2 is 3. So this is the same as f of 3. F of 3 is 2 times 3 minus 1. You just need to replace x with 3. That gives you 6 minus 1, or 5. What about f of a plus 3? So here, x has to be replaced with a plus 3. Whatever value you have here within parentheses, you're gonna replace x with that value. So here, you're gonna replace x with a plus 3. That will give us 2a plus 6 minus 1, that is 2a plus 5. So that was for part A. I'm going to do part B here. So that was part A. For part B, you're not given the input, you're given the output. You know that f of x is -11. So what is x that causes f of x to be -11? So f of x is negative 11, it means that 2x minus 1 is negative 11. We just need to solve this equation. That means 2x is negative 10. That means x is negative 5. So it's the value negative 5 as input that creates negative 11 as output. Let's check that. F of negative 5. That's 2 times negative 5 minus 1, which is negative 11. So right. So it's the value x equals negative 5 that produces negative 11 as output from this function. Part C asks for the domain of the function. So if you look at function f of x equals 2x minus 1, there is no real value that you cannot plug in here. You can plug in negative values, you can plug in 0, you can plug in positive values. So all real values can be used as input to this function. This means the domain of this function is all the real numbers, or r, which can also be represented as an interval from negative infinity to positive infinity. Another example. Find the domain of this function, f of x equals x over x minus 5. So before we find the domain, let's check what kind of values I can input to this function. For example, can I input 1 to this function? That would give me 1 over 1 minus 5. That is 1 over negative 4. Yes, so f of 1 is 1 over negative 4. Can I input 0 into this function? That gives me 0 over 0 minus 5. That is 0 over minus 5, which is 0. So that also causes no problem. What about negative 1? F of negative 1. That gives me negative 1 over negative 1 minus 5. That is negative 1 over negative 6, which is 1 over 6. So f of negative 1 is 1 over 6. So is there any value that I cannot plug it into this function? Is there any value that if I plug into this function causes a problem? Yes, there is. 5. F of 5 is 5 over 5 minus 5, which is 5 over 0, which is undefined. So this means that you can plug in any value into this function except for 5, because 5 is the value that causes a 0 denominator, which is undefined. So the way you solve this kind of problem is that you form an equality. The denominator, in this case x minus 5, equals 0, and you solve that. This gives you x equals 5. So this is the value that is not allowed. So you say the domain of the function f is r minus 5. This minus here is the set theory minus, which means excluding 5. So everything except for 5 is valid input to this function. 5 is not valid input to this function because it causes a 0 denominator, as we saw here. Another example. Find the domain of the function h of x is radical 3 minus x. Okay, so the restriction we have with the radical functions is that whenever you have a radical, your radicand, in this case x minus 3, cannot be negative. So in order to find the domain of such functions, your radicand, in this case 3 minus x, has to be non-negative. That is, it can be 0, it can be greater than 0, but it cannot be negative. So you form this inequality and solve it. So this means that negative x is greater than or equal to negative 3. Multiply both sides by negative 1. That gives you x is less than or equal to 3. So the domain of this function is from negative infinity to 3, including 3. These are all the values that give you either 0 or something positive as the radicand. Anything greater than 3 will cause a negative number as the radicand, which is undefined. For example, let's look at h of 2. h of 2 would be radical 3 minus 2, which is radical 1, which is perfectly fine. That's fine. What about h of 3? h of 3 is radical 3 minus 3, which is radical 0, which is 0. No problem. What about anything greater than 3? For example, 4. h of 4 would be radical 3 minus 4, which is radical negative 1, which is undefined. When you have a radical with an even index, the radicand cannot be negative. So that's why I have to, in the first place, I have to say the radicand 3 minus x is greater than or equal to 0 and solve for that. That will give me all the values that are valid input to this function. Anything from negative infinity to 3, because these are the values that give me a non-negative radicand. Another example. Find the domain of g of x, where g of x is x plus 1 over radical x plus 5. So again, we see that we have a radical. So this means that x plus 1, which is the radicand, cannot be negative. But here you should notice that the radical is in the denominator, so it cannot even be 0. So this is the equation that we have to solve. X plus 5 is greater than 0. Notice that in the previous slide, when we had a radical x minus 3, we solved for x minus 3 greater than or equal to 0, because you can have 0, no problem. You can have h3 that is 0. But in this other example, the radical is in the denominator. Since it's in the denominator, it cannot be 0. So 0 as the radicand is not accepted. Normally it is accepted, but because now it is in the denominator, it is not. So we solve for x plus 5 is greater than 0, and we don't have the equality sign. This means that x is greater than negative 5. This means that the domain of f is from negative 5. I have to use a round brace here to indicate that negative 5 itself is not included, to positive infinity. So for example, negative 3 is valid input. Let's check that. G of negative 3, that is negative 3 plus 1 over radical negative 3 plus 5. That gives me negative 2 over radical 2, which is perfectly fine. But 5 is not accepted input to this function, because, for example, g of 5, that gives me 5 plus 1 over radical 5 minus 5. No, this is accepted input. I mean negative 5. Negative 5 gives me negative 5 plus 1 over negative 5 plus 5. Now you see I have negative 4 over 0, which is undefined. So that's why here I have a round brace. That's why here I don't have equality, because negative 5 will give me a 0 denominator, which is undefined. So anything greater than negative 5 is okay, but negative 5 or anything less than negative 5 will cause either a negative number, either radicand, or like in this case, a 0 in the denominator, which is bad. So that's the domain of the function. So generally, if you have a radical in the denominator, you solve for radicand, in this case x plus 5, greater than 0. And that's it for intro to functions.